All right, Verge, hi.
Hi,
Welcome to
Mark.
welcome to 7.7 take 2.
Welcome to everybody who's tuning in live and folks who are watching us later today or even in another day, especially to our students. We really appreciate you coming and watching live.
I am still Mark Corrali from Ryan High School in Denton, Texas.
And I am still Verge Cornelius from Lafayette High School in Oxford, Mississippi. I have these new things on, so we're going to see if that helps to not blip out so much during the broadcast. I am not a gamer in terms of like zoop, 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 this kind of gaming, so I don't know what
As
I'm
illustrated
doing.
by the fact that she thinks that's what gaming looks like.
I mean, I play games, but not like video games. So these headset things, I feel like I'm wearing earmuffs and it should be 20 degrees outside. But anyway, enough about that. Let's see what we're doing these next few weeks and what we're doing today.
All right. Okay, we're halfway through our differential equation week. It's Wednesday, I believe. We'll see in a minute when Verge confirms that for us. We'll be finishing up differential equations. Next week, we will look at Unit 8, which once again on the 2020 exam, maybe not as important, but we will tie it back to previous units and start building in for our review, which will be the remainder from April 13th through May 1st.
And this slide right here, we have one full day without any corrections or oversights that we need to address.
It was our second day, just not in a row.
That's true. We're going to count these as consecutive days. And many of you watching, especially our AP colleagues from Kansas City readings, probably know who's trying to photobomb there. This was actually a picture taken at a College Board information session at one of the AP readings, I don't know, 5 years ago. I had different glasses, so it was definitely a while back. And I look younger.
I was going to say I think that's pre my daughter because I have less gray hair.
That's a good point.
and just a clue for those of you trying to figure out who the red-nosed guy back there, and that's a red nose for my dot, not for, we'll give you the hint, San Diego. So.
Yep, everybody knows who that guy is actually. All right, so for the March 32nd, 2020 class, we took care of the introductions and corrections. We're going to go ahead and do a warm-up in about 30 seconds. And then we're going to continue on with particular solutions to differential equations, try and wrap a little bit of guided practice into that using that technique of separation of variables. And then finally, some further resources, what you might find in that Dropbox. Mark, did you put stuff in the Dropbox already for those watching live?
I did. There is a key to yesterday's circuit, which I will preface by saying I only included that because I had it. We're doing another circuit today, and that is in there for particular solutions. And that is Verge's circuit. I don't know if we'll have a key in there tomorrow because Verge and I both believe we usually don't make keys for circuits. They should be self-checking. So you know what answers are out there. You can try to find it and kind of use process of elimination to find your errors.
All right, so this warm-up is from yesterday, and the directions are, which of the following could be a solution to the given differential equation? And the differential equation is dy dt equals 3t squared y plus 3ty, all divided by y. There are three choices, and we kind of did it in a multiple choice format as we decided how to present this. So D is none of these. That could possibly be the answer. And go ahead, if you're watching later, you can pause your screen right now and work it. We're going to give you about 45 seconds, those of you watching it live, and you can kind of locate
and if you did
work.
this yesterday, this was number 10 in yesterday's circuit.
Yeah, if you picked up where I kind of left off, you probably came across this one pretty quickly. I'll tell a joke for the remainder of the time so that we don't have quiet airtime.
Okay, before you start,
go ahead, Mark.
I want you to remember what the punchline is, and
yeah,
hold that back.
I have them all written down. Actually.
Okay, excellent. Okay.
Yeah, and so here we go. All right, it says, why can you never trust a math teacher holding graph paper?
Ooh, why can't you trust a math teacher that's holding graph paper?
She's obviously plotting something. All right. All right. And Mark, go ahead.
All right, I will
You
prepare
go-
to steal the screen.
Okay, Mark's going to work this problem for us. So go ahead, Mark.
All right, so I've got my circuit from yesterday here, and we got to scoot some stuff around on my screen. Okay, so when I start this one, my initial reaction to that divided by y, when I have a single denominator, is instead of dividing by y, I'm going to multiply by the reciprocal 1 over y. You know, unlike, you know, if there's a couple terms down here, we have some difficulty, but if it's a single denominator, breaking up is not hard to do. So we're going to distribute, and 1 over y times 3t squared y is going to get me 3t squared. And 1
Nice
over
pen,
y
by the
times
way,
3t
Mark.
y is, these are excellent. These came in the mail. It's
Mhm.
amazing. I have such wonderful friends,
Mhm.
particularly ones that teach at, I believe it's Lafayette.
We'll practice that tomorrow.
Oxford, from Oxford, Oxford, Mississippi, not the other Oxford. All right. And I did, oh, look at that. I get to take advantage of the eraser because I miscopied a T.
What in the world? Why isn't it? Oh, there it goes.
Pressure issues. Actually, it's funny. I didn't do that on purpose, but I do that on my chalkboard all the time. Drive kids crazy where I don't actually erase when they want me to erase things. All right. So it looks like the y variable's gone away completely here on the right. So I can separate. And now I have that dt on my right-hand side. Integrate both sides. And the 3t squared is the derivative of t cubed. And then 3/2 t squared plus c. And on the circuit, then that's what I'm looking for. But if we come back over here, try to remember that one there and put that in the back of your brain for about 7 seconds.
It's a trinomial.
T
I can
cubed
see
plus
that.
3/2 in a third degree, right?
Third degree trinomial.
And we have one candidate. Roman numeral 3 is our correct answer there. And it is a possible solution, right? This says could be a solution. We're not sure if that 7 is going to be for ours, but they didn't give us a point, so it absolutely could be.
Good. All right. Thank you, Mark.
You're
I'm
welcome.
going to go ahead and grab the screen now. And with my new setup, I have a slightly different. Oh, no, it actually worked.
Excellent.
Yeah, okay. So today is Wednesday. As I said earlier, before I leave my desk every night, I write down what the next day is going to be so that when I wake up, I don't have to ask Alexa or anything like that. I can just look at that and say, okay, this is what day it is and this is what we're doing. So this is our day 2 of finding solutions to differential equations. You saw this yesterday. Perhaps you took a screenshot of it or copy down notes. I know I have some of my own students who are being very diligent about copying lots of good notes so that they can use them on their quizzes when they take them. It's a whole new world with open note quizzes and things. But in any case, some differential equations can be solved by separation of variables, and anti-differentiation can be used to find solutions to differential equations. These are some of the skills that we're really working on here. Mark, were you going to say something?
Did you want that other slide there before you come to this, or we had the other slide with the particular versus general solution?
We can go back to that in just a second.
Okay, that's just
yeah.
want to know when you wanted me to insert it.
Okay, yeah, we'll come back to that in just a second. The general solution, if we're trying to find it, the process, and Mark actually kind of talked through this, the process would be to separate because we're working with only separable differential equations. Integrate, he nicely said, I'm going to integrate on both sides, and then solve for y. Algebraic, that's algebra part of the whole deal. The particular solution means that we're really finding the specific solution curve that goes through a given point. So for all the examples today, we're going to have a little bit more information because we're still going to separate, we're still going to integrate, we're going to solve for c given that point, and then we are going to ultimately solve for y. So that's a little bit different on the flow. Mark's going to show the one from yesterday, if you want to go ahead and grab the screen, Mark,
Yeah.
which was the slope field that had all of those circular slope field. And when we were preparing that lesson, I very quickly figured out the particular solution through that point, -2, 5. And yesterday I didn't, yesterday I said, don't worry about this. We aren't doing this today, but actually today, now we are doing this today. We are going to figure out how to solve that differential equation, dy dx equals -x/y, and find that particular solution going through the point -2, 5. Okay, now when I woke up this morning, and I'm going to go ahead and grab this back
Yes,
again,
please
Mark.
grab it back.
Yeah.
Make it so.
Make it so. When I woke up this morning, I was thinking about a couple of different things. And one of the things I was thinking about was that, and all teachers do this, I felt like I didn't do a great job teaching yesterday. And so I thought, what did I do? Why did I forget that really important piece of my teaching when I'm teaching differential equations? And here it is. So again, some real high-tech stuff going on here. But if we're going to solve differential equations and find particular solutions to differential equations, one thing that mathematicians do is they automatically think to themselves, what is it that I have? What is it that I'm looking at? These are three very different differential equations, because in this case here, dy dx equals x² + 4, only the independent variable is showing here on the right-hand side. Only the x is showing. Whereas on this one right here, dy dx equals 3y, only the dependent variable is showing on the right-hand side. And then finally, and this kind of reminds me of the dy dx equals -x/y, both the dependent and the independent variable, the dependent and the independent variable are showing here, okay? This is an important thing as you strategically go through that separation, because a lot of times students will misinterpret which variable is which, particularly when you have not x's and y's. So if you had something like db dt equals b cubed, now my x and y's are gone, and now I have to really think to myself, okay, is this differential equation more like this one, where just the independent variable is showing, this one where just the dependent variable is showing, or this one where both are showing? Mark, what do you think?
No, I think that's excellent. And I also want to point out this ties back very closely to what we were
Well, I
doing.
was actually asking you what you thought the answer was, but
Oh, what I thought the answer was. I just wanted to interject.
both. You can do both. Go ahead and tell me what you think.
You cleverly put that green Post-it right behind my little floating box of your face. So it looks like b is in the same slot on that derivative expression as y would be. So it looks like b is a dependent variable to me.
Mm-hmm. And then that's
because we're doing with respect
cubed
to t. So b is an implied function of t, or at least an implied relationship of t.
Yes, exactly. And those of us who have taught for a long time and seen student errors, we know that this is common, where students will misinterpret this and think that, oh, they imagine this as more of a t cubed, and then they go from there, and they don't separate correctly. Yeah. Okay.
And both as a student, when decades ago, when things like this would come up, what Verge has written here side by side is exactly what I would do. I would go over in the margin and write, y prime equals dy dx, just to remind myself of where the y lives and where the x lives.
Mm-hmm.
I mean, obviously you get to a point where you're more fluent, but just writing that more familiar form of the derivative on the left side, and then going, okay, what role is the b playing? What role is the t playing?
So you can structurally kind of match them up and know kind of what your plan is going to be. Okay, so my
plan.
Then
I am going to interject again. I'm not going to ask permission, because yesterday you got me on that.
Yeah.
But I was going to say that just also ties back to the analysis of slope fields, both what they're going to look like in matching games that we were playing on Friday and Monday, that identifying those independent and dependent variables can also lead you to have a picture of what's my solution going to look like before I get there. Much like in algebra, when you get an answer, is it reasonable? Does this make sense?
Mm-hmm. Exactly. Because if in the beginning you're thinking about it, then in the end, you know whether you did it right or not. So we're going to work a lot of problems off of this circuit, which is a circuit I wrote about 5 years ago called differential equations. And I'm not going to work them in the same order. So take good notes, because when you print this for yourself or when you look at it for yourself, you can kind of go back and fill in some of the gaps. But I've intentionally picked certain ones that I want to work on today, and then other ones that we will work on tomorrow in that 7.8 unit or section. So this one here, the directions are the same. Find the particular solution to the differential equation given. And we know this little bit of information about it as well. This is a point that the solution curve is passing through. This should look very familiar. This is the one with that circle, or the top half of a circle that we worked on yesterday and the day before. So in this case here, when I look at dy dx is equal to negative x over y, I see that both the independent variable and the dependent variable are showing, and I make kind of a mental note of that. So that means that I'm going to go ahead and separate first by getting the y over with the dy and the dx over with the x. So I get y dy is equal to negative x dx. Then I'm going to integrate on both sides. So I have the integral of y dy, which is going to be 1/2 y squared, is equal to the integral of negative x dx, which is going to be negative 1/2 x squared plus c. And we spent a long time yesterday talking about that c value just being on that one side. So if you're just tuning in for the first time, you might kind of go back and watch that other video. Now I'm going to go ahead and use this point and substitute in -2 for x and y to be 5. So I have 1/2 times 5 squared is equal to -1/2 times -2 squared plus c. This is the way I do it personally. Other teachers might do it slightly differently, multiplying both sides by 2 or whatever first. But notice in my directions, I said I separate, I integrate, I find my c value or solve for c, and then I find my y value. I don't know why this is flashing so much. Maybe I'll try and press that and see if that works. All right. So in any case here, I have 25 over 2 equals, this is going to be 4 times -1/2 is going to be -2 plus c. And so make sure I'm right.
I think you're okay. I almost corrected you and said -4 over 2.
Uh-huh. -4 over 2. Yeah, that would have been easier, because now I have to then write it as -4. I'm getting 29 over 2 for my c value. Okay. So I have now 1/2 y squared equals -1/2 x squared plus 29 over 2. So I'm coming back to this line right here, and I'm rewriting that line and substituting in the 29 over 2. Now I'm going to go ahead and solve for y. That's my last step. Multiply both sides by 2. So I have y squared is equal to -x squared plus 29. Take the square root of both sides. I'm doing just algebra right now. So y is equal to plus or minus -x squared, or sorry, y is equal to plus or minus the square root of -x squared plus 29. I'm going to do like on the board, I have to kind of come up here. And then I need to make sure to decide whether or not I pick that positive branch or the negative branch. And I'm going to pick the positive branch because my input of -2 needs to yield an output of +5. So I need to pick that positive branch. That's the particular solution. That's exactly what we had in that earlier slide. Might look a little different because addition's commutative, but in any case, that's the top half of the semicircle. We might even talk about the domain. Mark, are you interested in talking about the domain?
Sure. Let's see. So our domain is going to have to be, we're going to look at,
we knew that we had this, right?
Right, because we have a radical. So we're obviously, our interior has to be greater than or equal to 0. So the radicand, the negative x squared plus 29, has to be greater than or equal to 0. And then the reason we have the open holes at the ends is because this actually is y equals. And so from the original differential equation, y cannot be 0, or that is undefined. So we don't know what happens at those endpoints. If they may be included, they may not be, but their derivative doesn't exist there, so we just don't know.
So I'm thinking my
So I'm
domain
looking
would be like
square root of negative square root of 29 to 20 square root of 29. That sounds
something
good.
like that, and you can write it in interval notation if you wanted to, of course.
Yes. So
Yep. Okay.
And again, this actually came up on the AP community today, and I've sent a counterexample to someone that disagreed with me on including the endpoints, but I haven't gotten a response.
Okay, maybe that person's listening and watching with us
Maybe,
right now.
perhaps.
We'll
And
find out.
I respect his opinion, so he may come back with a counterexample that makes me go, oh, you're right.
Yeah, we learn stuff all the time from each other.
So I was gonna, do you mind if I steal it for a sec?
Yeah, go ahead.
Let's see. This one. So this is my version. And this is what Verge was saying. Some people do it different. Some people solve for the y, then plug in the c to find the c. Verge and I both are in the camp where we're plugging in right away. But the one thing I did do a little different is in Verge, I know this is going to just blow you away. I have students that don't like working with fractions.
Oh, that part. Yeah. Okay.
Yeah. And so, so a lot of times I multiply both sides by 2 right off the bat, which then became, so this was just my y squared and then the opposite of x squared plus c. So I end up with my c was 29. Now,
that is so much cleaner than mine. I like
my
it.
c is twice of Verge's c, and this is, so like I said yesterday, when you double the c, it's still c, but our c's are specific to our equations now. So when I come back, I have the y squared equals the opposite of x squared plus 29, and then everything else follows, you know, of course, because math works, and that's one of the things that makes it so wonderful.
Right. And notice how our final result was the same, exactly. Yes. Even though the middle part, the peanut butter and jelly part or whatever, looks a little bit different. All right, here's our second example. So our second example says dy dx is equal to 2x, and then y of 1 is equal to 7. A little bit of a different presentation on that initial condition or that point on the solution curve. Some people might like to write it as 1, 7 so that they're not as confused by which one's the x and which one's the y, since the y is right next to the 1 right there. In any case, I'm going to go ahead and separate, but before I do, I'm going to think to myself, what am I looking at here? I'm looking at, oh, just the independent variable is showing. Okay, so when I separate and I have the dx on the other side, I have dy is equal to 2x dx. And Mark yesterday said that sometimes he puts a 1 right there to help students remember the integrand is just 1 in that case. So antiderivative of 1 with respect to y would just be y is equal to, now I'm integrating, integral of 2x is going to be x squared and then plus c. Substitute in the 1 for x and the 7 for y. So I get 7 is equal to 1 squared plus c. And then c ends up being 6. So my particular solution is y equals x squared plus 6. Again, if you work the circuit, what you're going to end up having to do to advance in the circuit is then find another, like there's a little kind of a treasure hunt kind of thing going on where there's a little extra thing you have to do at the end. You'll know what I mean when you take a look at it. It's very fun.
Make sure you read the directions because she doesn't want you working it backwards by taking derivatives.
Yeah, I don't know why this is flashing. Okay, so in my typical classroom situation, I would give a couple of not so hard ones at first, and now it's like, okay, we're getting real now. So in this example here, number 3, dy d
it's
theta.
A tricky one.
It's so tricky. We're gonna get tricky with it. dy d theta is equal to 4y squared secant squared of 2 theta. And then here's my given information, similarly given as before, y of pi over 8 is equal to 1. So we've got the point 1 comma pi over 8 on our solution curve. Now, here's the thing is that there's a lot going on here. First cut, I see my y and I see my theta. So both variables are showing. I need to separate these off, get the y's with the dy and the theta, d theta over here. So I'm going to go ahead and leave the 4 actually over with the secant squared. You can do what you want, but that's what I usually do.
It's
So
bizarre because I'm doing it right now, and that's what I'd already done.
Yep. So first step, separate. So I have dy divided by y squared is equal to 4 secant squared of 2 theta d theta. I might write this as y to the negative 2 dy and getting kind of ready to integrate there. And then with my 4 secant squared of 2 theta d theta, I might insert my integral symbol there, sliding that coefficient out so that I can more carefully focus on that integrand. If you were watching yesterday, you know that I always do the easier part first. And so to me, this is the easier part. I'm just going to add 1 to my exponent and divide by my new exponent. So I get negative 2 plus 1 is going to be negative 1. So I have negative 1 y to the negative 1 or negative, well, you could have it written a lot of different ways. In fact, okay, reality, I would probably write it like this because I kind of have that memorized. But reverse power rule, this might be an easier, leap from there to there. All right, on this one, the integral of secant squared of 2 theta, you really kind of need to think about a u substitution here, perhaps, unless your teacher has had you memorize some chain rule or u substitution with just a linear coefficient in here. So it kind of depends on how you've memorized things. And memorization is not a bad word. I want to say that, especially when it comes to trig. Sometimes you just got to do what you got to do. So I think my students, for example, probably have this written somewhere on their yellow sheet, which is nothing fancy. It's a yellow sheet of paper where they write all their formulas.
Very clever.
Yeah, it's great. It works really well too. We build it throughout the whole year and they have this great yellow sheet now.
I look forward to the year you run out of yellow paper and everyone's yellow sheet is blue.
Yeah, so yeah, that won't happen. But anyway. And when I taught trig, though, I did have several different colors, but you don't need several different colors for calculus. Yes.
I just got a text. I don't know if you can slide it down a little, but apparently that the initial condition is under your picture. It may actually, it's not anymore because you moved it over.
Okay. So. All right. I'm just going to go ahead and write this general rule right here that the integral of secant squared of k theta d theta is 1 over k tangent of k theta plus c. Okay, instead of doing a u substitution here, that is probably how I would deal with it. And so in this case here, my k value is 2. I'm going to slide this back over again. I'm trying to keep everything in the view. The k is 2, so I'm bringing down this 4, but just kind of ignoring it. So 4 times 1/2 tangent of 2 theta, and then plus c. So I would not do a u substitution there. Again, different teachers are going to do things a little bit differently. So 4 times 1/2 is 2. So I have 2 tangent of 2 theta plus c is equal to negative 1 over y. I'm going to go ahead and plug in my pi over 8 for my theta and my 1 for my y. So I have negative 1 over 1 is equal to 2 tangent of 2 times pi over 8 plus c. 2 times pi over 8 is 2 pi over 8 or pi over 4. So we're looking at tangent of pi over 4. What would that be, Mark?
Well, pi over 4, a lot of you like to think of that as a 45-degree angle. Tangent of a angle is the slope of the resulting line segment, right? So, and you gotta scoot your picture up a little bit. So I'm thinking that's 1. I think a pi over 4 ray has a slope of 1.
Good. So negative 2 equals 2 times 1, which, ooh, that's my bad. Hold on a second.
Good catch, good catch.
Yeah. So -1 equals 2 times 1, which is 2 plus c. C is going to be -3. So again, bringing it up here, C value is -3. I need to come to this line right here and then solve for y. So -1 over y is equal to 2 tangent of 2 theta plus -3 or -3. And then to solve for y, I don't need to take the square root of both sides this time. I do need to reciprocate, like that's how I would do it.
Yep.
Some people might multiply both sides by y and then divide both sides by this stuff. A couple of different ways to do it, but pretty much y is equal to -1 over 2 tangent of 2 theta minus 3.
That's what I got.
Yay! That's a lot.
Yeah,
like you need to practice that on your own. Yeah, go ahead, Mark.
Couple things I just want to point out, because I did get a couple text messages from our teacher friends. If you just slide the original down,
Sure.
just if people are wondering where that point came from, and it kind of goofed in and out of place because our pictures are in that corner. We can't see our pictures in the corner, so we need to remember that, I suppose. So that initial condition was given in the original problem, that y of pi over 8 is 1. And then I want to talk about the second to third line of your work, of just, if you did the worksheet from yesterday, if you start doing what we're going to be playing with for the rest of the week and what we've been playing with the last 2 days, you're going to get into this idea of, hey, y is in the denominator. I'm going to get a log. And
ooh, this is an excellent point.
And so
okay,
you really want to make sure that if that is not of that form, dy over y or dy over y plus a constant, that you really analyze it. And, obviously Virg and I are a little more experienced. So she, without a blink, went, oh, that's y to the -2. I'm going to do a power rule. So one, you don't want to fall into a log trap, and you don't want to fall into a power rule trap, right? You have to investigate that, because if you try a power rule with y to the -1, you're going to be dividing by 0, and then you for sure know something has happened.
That's right.
But I just wanted to point that out, that our demonstrator here did an excellent job of not even looking at that trap. But it is something, just to repeat what Virg just said, you're going to have to practice some of these. It's really easy to watch us do them and go, oh yeah, I can do that. But to get the experience of watching for things like that, I think it's important that you do some of these on your own.
And actually, speaking of doing things on your own, this morning when I was getting ready, and I've been doing calculus for a long, long time, but this morning when I was getting ready, before Mark and I even met, I worked all these problems, and I've done them lots and lots of times, but I worked them all just to make sure, practice it, so make sure I could do it. All right. This one is one that we were hoping that you guys would try and get a head start on anyway. I don't know why it's flashing so terribly. Okay. It says dy dt is equal to -2t divided by y. And the given information is that y is -6 when t is equal to 0. So those of us going live, we're going to do kind of wait for you to get a 30-second head start on us. Those of you who are watching later, you can pause it right now and try and work. This would be a good one to try and work. It's not as hard as the previous one. And Mark, if you want, you can reveal your slide.
Yeah.
In about 10 more seconds.
Oh, no pressure, because I'm not like Virg. I wing it a slightly bit more. So we have
that's good. That's because I have to you got the smarts and I got the, I don't know what I got.
We'll go with it until I make a mistake. All right.
Okay. You got it. It's okay if you're not all the way done. You can reveal.
No, dang it, no. All right, got it.
Okay.
I was having to think about which fork I needed, so you can call me out if I got it wrong.
Okay, that's a good point.
So, and I'm doing 2 columns on the right side of this page, so let's get this. All right. Did I copy it right? Because that's super important.
Perfect.
So dy dt is -2t over y. 0, -6 was the initial condition, although you had it written as y was -6 when t is 0.
Mm-hmm.
So I multiplied my y over to the left, used my differential rules to get negative 2t dt on the right, doing my antiderivatives of both sides, get 1/2 y squared, have a cursor in the way, get negative t squared plus c on the right, because I just did a power rule, so the 2 up there and then divided by 2. And then I brought in my initial condition at 0, negative 6. Negative 6 squared is 36. So I got 18 for c. Went back to my initial antiderivatives and plugged that in. And then I got told I had to share. So I doubled both sides. I got rid of that half, multiplied that by 2, multiplied 18 by 2. And then to solve for the y squared, I took the square root. I realized this should be a plus or minus, but my initial condition, if I plug a 0 in there, I get square root of 36, which is 6, because this is a principal square root. So I need that negative to force that answer to be negative 6.
You have the correct answer, Mark. Great job.
Yay. I also want to compliment you on the consistency of your y's.
Oh, yeah?
Because I actually have 3 y's, and there is no rhyme or reason between when I change. So if you notice on this one with the secant squared, I went from curly y to straight y between lines, and I can't make myself not do that consistently. I have no idea. So if anyone out there is studying AP Psych and can find out what it means if you mix your curly and straight y's, I would love to hear from you.
Yeah, we could do a whole entire lesson on handwriting and math, because you really have to be careful when you're writing Y, when you're writing X, when you're writing T, that your handwriting is legible, not only for you, but also for anybody who's reading your work. Here's our fifth example. This is another one we'd like you to try. That means you, Mark.
Thanks.
You're my only student right now. But it's dA dt is equal to t plus 4. And then a of 2 is equal to 11. So I'm going to go ahead and give you about 30 seconds, Mark. And no pressure. Those of you who are watching it live can at least get a head start. You might not be able to finish it, and that's okay. Those of you who are watching it later can pause right now and try and finish this out. Think about the questions that I was asking before, like A is my dependent variable here, T is my independent variable. You could even translate this into X's and Y's if you wanted to. Like Mark was saying on the side, he writes a little dy dx equals y prime or whatever. So, okay, Mark, what you got?
I have got my last line coming in right now. Okay. In a clean sheet of paper. And I appreciate that someone keeps texting us that when the initial condition is behind Verge, but I'm not, we're just going to have people listen. All right. So I separated my dA on the left. I went ahead and threw a 1 in there for myself. Have t plus 4 dt. Came in with my integration. Got a on the left, 1/2 t squared plus 4t plus c. Plugged in 2. Half of 4 is 2. 4 times 2 is 8. 10 plus c has to be 11, so c is 1.
That's
and
what I got.
This quadratic. Yay.
Yeah, so your solution, and there's no choice in that case, because when you're solving for y, which in this case is a, you didn't even have to do anything algebraically, so you didn't have to pick a branch or anything like that, and you just had a parabola.
Yep.
Okay, and here's our last one, which I'm going to go ahead and work through. It is a little bit more challenging, but ones that I work through, like this one and like number 3, I guess it was, those are good ones to try and do later on your own and see if you can do them correctly without looking back at your notes. In any case, this one is xy dy, or sorry, let me restart that. This is number 6. Xy dy dx is equal to the natural log of x. And then given information, y of 1 is equal to 2. So in this case here, if I'm looking at what my given information is, I see that I've got natural log of x, I've got x, I've got y, I've got both my independent and dependent variables are given here as part of this differential equation. So first step is to separate. I'm going to leave the y with the dy, but get that x over to the other side, and also get that dx over to the other side. So I'm going to have to divide both sides by this x to move it to the other side. So I have y dy is equal to natural log of x, all divided by x dx. Don't be tempted to cancel these out. They're not going to cancel out. Okay, integrate. So I'm going to go ahead and integrate y dy first, reverse power rule, add 1 to my exponent, divide by my new exponent, or multiply by the reciprocal of that exponent. So 1/2 y squared equals, and then this one right here really is a U substitution. I don't really have a rule memorized in my head for that. So I might kind of go ahead and think about it on the side, or I might even think about it right underneath, but not put equals because that will make me nervous. I'm going to let U equal the natural log of x. And then du dx would be 1 over x, or 1 divided by x. So, and this is what we do in my classroom. I say that x du is equal to dx. And then I rewrite this integrand by substitution. So I've got the integral of u in the numerator divided by x, and then times x du, so that these x's divide to be 1, kind of cancel out. So I have the integral of u du, which is going to be 1/2 u squared plus c. This is all kind of like thought bubble. It's not really in terms of x, but I'm going to use that result based on what my original integrand was. So I know that u is equal to ln x, so the integral of this integrand is actually going to be 1/2. So I'm going to go ahead this down. I'm sorry, my initial condition is disappearing. 1/2 1/2 y squared is equal to 1/2, and then natural log of x squared plus c. So I'm sorry that it's kind of blipping out here, and I can tell that that's happening because I'm getting an alert message. I think it's my provider. Everybody's on their internet in Oxford, Mississippi right now, I guess. In any case, so my natural log of x was my u. I substituted it in there. And so now I have 1/2 y squared equals 1/2 natural log of x squared plus c. Y of 1 is equal to 2. So I'm going to bring this up here and use that initial condition to find the c value. 1/2 times 2 squared is equal to 1/2 natural log of 1 squared plus c. 2 squared is 4 times 1/2 is 2. Natural log of 1 is 0. Half times 0, well, 0 squared is 0. So I'm getting c value to be 2.
That's what I got.
So rewrite 1/2 y squared equals 1/2 in parentheses natural log of x squared plus 2. Solve for y. Y squared multiplying both sides by 2 equals natural log of x squared plus 4. And then take the square root of both sides, get y is equal to plus or minus the square root of natural log of x squared plus 4. Which branch do I want? That depends on the output of your initial condition, or kind of. I mean, like, you have to do an input output and make sure you reconcile the branch that you need, and we need the positive branch this time. So the final answer is y equals the square root of natural log of x squared plus 4.
And again, the reason part of the reason we reconcile those branches, if you remember yesterday, was that we're always looking for a function solution, right? And up until then, that was not a function. It was a parabola opening to the right, I believe.
Okay, something for sure.
Or no, I wouldn't even. No, I take that back completely.
Composite function.
Yeah. The outer function is a parabola, but yeah, it's a composite. So I retract that.
Yeah, who knows? But I think that's all we have time for today. We don't want to keep you too long, and we're going to go back to the PowerPoint and just kind of do a little bit of wrap up. We really encourage you to work on those resources provided. Your teacher might have some ideas. Maybe you'll do them together in your own classroom setting virtually and work through them and discuss them further. Or you might be kind of on your own doing it, and wow, you're amazing if that's the case. We really, really applaud you. Even if one person's watching, we're doing it for that one kid who's working their tail off.
Absolutely.
And we'll be back tomorrow, and we're going to work a lot on the exponential function tomorrow in terms of its differential equation and what model that goes to. So anything else, Mark, as we wrap up?
No. Again, just a reminder, you can pause this if you need to. We're not going to go through the whole thing again, but we still, if you have friends in need, or yourself or relatives, whichever, and you need the connectivity or devices, please let College Board know at cb.org/tech. And of course, that bit.ly that's been in the description below the video every day has our folders. And the way the folders are organized is if we refer to it in that video, that's the folder it's in. So.
Okay.
All right. Thanks, Verge.
Okay. Thank you, Mark. And we'll see everybody tomorrow.
Bye.
Bye.